Hello everyone, I am MD Monir Islam. I just graduated from the Big Data Analytics Laboratory at the New Jersey Institute of Technology. This problem is part of my PhD dissertation and a joint work with my former lab members Dong Wei, Professor Baruch Shiver, and my advisor Shenjuti Basurai. The work I will be presenting today, titled Satisfying Complex Top-K Fairness Constraints by Preference Substitutions. This is the overview of the talk. This work derives motivation from a plethora of applications that arise in the context of search and recommendation. The input assumes that a large number of users have provided their top 1 preferences, and the output intends to find the top k set of results that are most representative. Naturally, when the users provide their top 1 preference, plurality voting is a natural choice to aggregate their preferences and choose a set of top k items that have the highest k user preferences. As an example, given 12 voters and their preferences over 6 candidates, the plurality voting will select candidates C1, C2, C3, and C4 as the preferred top 4 candidates as they have the highest number of votes, that is, top 1 preferences. However, we study the problem in the context of complex query constraints that may be important when the constraints intend to satisfy fairness criteria. As an example, imagine that the candidates in the dataset have 3 protected attributes: gender, seniority level, and marital status. Here, gender and seniority level are binary protected attributes because they have 2 possible values, and marital status is multi-valued protected attribute with 3 possible values. The fairness criteria imposed by the query intends to ensure that in the top k results, there exist 2 male, 2 females, 2 juniors, and 2 seniors, 2 married, 1 single, and 1 divorced. Clearly, C1, C2, C3, C4 does not satisfy these constraints because in that case there are 3 men and 1 female, 3 single and 1 married, 3 junior and 1 senior in the top k. This requires us to change the original input preferences. However, the original preferences of the voter should not be changed arbitrarily. This needs to be done carefully such that the number of changes are minimized, and based on the modified preferences, the plurality voting selects the top 4 candidates that satisfy all query constraints. As an example, if one removes 2 votes from candidate C2, such as V3 and V5 now prefer C6 as opposed to C2, and similarly remove 1 vote from C4, such as V10 now prefer C5 instead of C4, then the changed preferences while being aggregated by plurality voting give rise to C1, C3, C5, C6 as top 4 candidates. It is easy to notice that these 4 candidates satisfy all fairness constraints defined over the 3 protected attributes. This very process of taking 1 vote from candidate I and giving it to candidate J is referred to as ballot substitution. The example in this slide requires 3 ballot substitutions to satisfy the query constraints. Formally speaking, we study the margin finding problem, which is to find the minimum number of ballot substitutions to satisfy query constraints. We study several variants of the problem, considering if the query constraints are defined over 1, 2, or 3 or more attributes. When single attribute is considered, we study both cases, one with binary protected attribute, namely MF binary S, and the other with multi-valued protected attribute, namely MF multi S, because these 2 variants require different algorithmic treatments. Also, there is reason for studying 2 attributes and 3 or more attributes cases separately, as the nature of the problem changes between these 2 cases. The later 2 problems are defined as MF multi 2 and MF multi 3 plus respectively. This slide also enlists the name of the algorithms for each of these variants accordingly. In terms of positioning our work, there are two types of related work that require attention. One is the context of subgroup fairness, primarily studied in the context of classification model to ensure that the false positive rates across subgroups are equivalent. This problem is deemed to be computationally hard. Contrarily, we study subgroup fairness in aggregating user preferences defined over multiple attributes to select top k. Additionally, we established that the margin finding problem for two attributes is weakly NP-hard, while determining the feasibility of fair outcome for three or more attributes is NP-complete. The other related work is the margin of victory problem, which is studied in the context of electoral voting mechanisms for techniques such as single transferable voting or STB. The margin of victory studies how easy or hard it is to manipulate a voting mechanism to change its original outcome. Orlin and Bartholdi proved margin finding is NP-hard even for a single candidate selection for STB. Contrarily, we study margin finding for plurality voting to satisfy fairness constraints. We propose a p-time solution for the margin finding problem considering a single protected attribute and prove that for multiple protected attributes, the problem becomes NP-hard. Given the time constraints, I would like to briefly leave some intuition about design solutions for one of the studied problem variant, namely MF multi-S. That is the margin finding problem where the fairness constraints are defined over a single multi-value protected attribute. The main intuition is the following: design a threshold T such that each of the top k candidates get at least T votes and one of the candidates gets exactly T votes. Then the problem becomes finding the T which minimizes the number of substitutions that is the margin. As an example, if one has to select of 4 candidates such that 2 are married, 1 is divorced and 1 is single, this requires a number of ballot substitutions. One possibility is to reduce votes from candidate C2 and C4 to 1 and increase votes of C5 and C6 to 2. This requires a total 3 ballot deletions from C2 and C4, and that 3 ballots are to be added for C5 and C6. Now, the resulting top 4 candidates are C1, C3, C5, and C6, which satisfy the query constants. Interestingly, the threshold here turns out to be 2, as there are the fourth candidate C6 now has 2 votes, and the other 3 candidates C1, C3, C5 have at least 2 votes. This is the intuition that is leveraged in this algorithm. The minimum and maximum possible T values in this example are 0 and 4 respectively. The T value which ensures margin, that is the smallest number of substitutions, could be found by making a binary search over this. I want to briefly discuss why margin finding to satisfy fairness constants defined over multiple protected attributes is hard, and why existing solutions do not study them with appropriate computational rigor. Existing work intends to assume that the attributes are independent and computes portions based on their highly limited assumptions such that the fairness constraints find solutions over a transform multiple protected attribute as shown in this slide. Clearly, the transform attribute and their corresponding portions does not satisfy the original query constraints. Before moving into the experimental evaluations, this slide summarizes our technical contributions. We designed p-time solutions for single binary and multi-valued cases. We proved for two attribute case, the problem becomes weakly NP-hard. We designed a two approximation algorithm L2ATTAPX for that. For more than two attributes, deciding the feasibility of the general instance becomes NP-complete. We designed a Cartesian product-based solution which runs in p-time considering constant size of Cartesian product of the protected attribute values. The corresponding running time of each of the algorithm is shown in the slide. Moving to our experiment section, our experiments are conducted using 4 real-world and 1 synthetic dataset. We have 2 goals of our experimental evaluations. The quality goal of the experiments is to focus on margin values of each of the implemented algorithm while ensuring the satisfy fairness constants. On the other hand, scalability measures the running time of the different algorithms by varying appropriate parameters. Two baseline algorithms adopted from related works are Leximin and Fair-Topke set. None of these algorithms solve the margin finding problem, but they are studied in the context of fairness. Leximin produces a probability distribution of a set of possible top k candidates, where each of the sets satisfy fairness constants. On the other hand, fair top k set first converts multiple protected attribute to a single multivalued protected attribute by computing joint distribution over the attributes assuming their independence. The fair top k set is a heuristic and it doesn't always give a feasible solution. For quality evaluation, the figure at the left side demonstrates that our algorithm for single attribute case outputs optimal margin while Leximin does not. And the figure at the right side shows that our proposed approximate algorithm has an approximation factor less than 2, while the exact solution LK2PT is optimal. For scalability solution, our results demonstrate that our designed solutions are scalable and perform better than the baseline algorithms. For example, in the left side of the figure, L280 is 2000 times faster than the Fair-Topke, and Leximin is not even scalable. Similarly, the right side figure demonstrates that our algorithm ALG180T BOPT and ALG180T MOPT are faster than Leximin and Fair-Topke set. The summary of our experimental evaluations are the exact algorithms produce the smallest margin while satisfying the fairness constants over 1, 2, or 3 plus attributes. Approximation algorithms demonstrate better empirical approximation factors compared to their respective theoretical bounds. Design algorithms are highly scalable. Existing solutions produce suboptimal margin values or even infeasible results for MF multi 2 and MF multi 3 plus, as it just became a heuristic for these problems. Integer linear programming based solutions do not scale as expected. In this research, we delve into the margin finding problem in preference aggregation involving single ballot substitutions. Our core aim is to attain fairness considering either one or multiple attributes of protected groups. We methodically investigate various problem variants encompassing diverse definitions of fairness constants such as binary multivalued attributes and multiple attributes. We formulate algorithms with variable guarantees supported by theoretical scrutiny and their efficacy and scalability through extensive experiments on real-world datasets. Thank you everyone for listening. Our paper will be presented on Wednesday at session F5 and the poster session is also on Wednesday. Please stop by.